NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will master an algorithm for solving logarithmic equations of the form log base g of f equals b, and then apply it to a concrete example. Here is the structure we will use. First, we display the target form. The golden rule says log base g of f equals b if and only if three things hold together. The base is positive, the base is not 1, and the argument equals the base raised to b. We'll box that as our algorithm. Now, let's apply the algorithm to a clean example. We will solve log base x of x plus 2 equals 2. Identify the pieces. Here, the base function g of x is x, the argument f of x is x plus 2, and b equals 2. Step 1. Enforce the domain constraints from the algorithm. Base strictly positive, base not equal to 1, and argument positive. For our base g of x equals x, we get x greater than 0 and x not equal to 1. For the argument x plus 2, we get x greater than negative 2. Step 2. Convert to the exponential equation. Argument equals base to the b. So x plus 2 equals x squared. Move all terms to one side to get x squared minus x minus 2 equals 0. Factor to get x minus 2 times x plus 1 equals 0. So the candidates are x equals 2 or x equals negative 1. Step 3. Check the candidates against all domain constraints. The candidate x equals negative 1 fails because the base must be positive. The candidate x equals 2 passes, all checks, so it is the solution. Final answer x equals 2. We followed the algorithm exactly. Enforce the base and argument conditions, convert to an exponential equation, solve, and then intersect with the constraints. Recap card. For log base g of f equals b, base positive, base not 1, argument positive, and f of x equals g of x to the b. Here is the problem. Step 1. Write the equivalent system exactly as shown in the provided solution. 1. The base condition x plus 1 greater than 0, which gives x greater than negative 1. 2. The base cannot be 1, so x plus 1 is not equal to 1, giving x not equal to 0. 3. Convert the logarithm to the algebraic equation by definition. The argument equals the base to the power 1. Step 2. Simplify the equation part of the system. The quantity x plus 1 to the power 1 equals x plus 1. Move all terms to the left to obtain a quadratic. Step 3. Solve the quadratic equation. Factor out x to get x times x minus 4 equals 0. Therefore, the candidate solutions are x equals 0 and x equals 4. Step 4. Check the candidates against the system restrictions. We need x greater than negative 1 and x not equal to 0. So x equals 0 is excluded, and x equals 4 is accepted. The final solution set is the singleton 4. Recap. We followed the given algorithm exactly. Wrote the system with base conditions, converted the logarithm to an algebraic equation, simplified to a quadratic, solved for candidates, and finally applied the restrictions to keep only 4. Therefore, D equals the set containing 4. Example. We will solve the logarithmic equation exactly following the listed steps. The equation is log base x of open parenthesis 2x squared minus 3x minus 4 close parenthesis equals 2. Step 1. Replace the logarithmic equation by its equivalent system. The base restrictions are x greater than 0 and x not equal to 1. And log base x of a equals 2 means a equals x squared. So the third line is 2x squared minus 3x minus 4 equals x squared. Step 2. Bring all terms to one side to get a standard quadratic. 2x squared minus 3x minus 4 equals x squared becomes x squared minus 3x minus 4 equals 0. Step 3. Factor the quadratic. X squared minus 3x minus 4 equals 0 factors as open parenthesis x plus 1 close parenthesis times open parenthesis x minus 4 close parenthesis equals 0. Step 4. Apply the zero product property. Therefore, x equals negative 1 or x equals 4. Step 5. Enforce the domain of the logarithm and keep only valid solutions. We need x greater than 0 and x not equal to 1. So negative 1 is rejected. Also, the argument 2x squared minus 3x minus 4 must be positive at any solution. At x equals 4, the argument equals 16, which is positive. Hence the solution set is d equals curly brace 4 curly brace. The equation is log base x squared of open parenthesis 2x minus 1 close parenthesis equals 1/2. First, as in the image, we list the base conditions only. We require x squared greater than 0 and x squared not equal to 1. Now write the original equation to begin the algebraic steps shown. Using the identity from the image, log with base x squared of a quantity equals 1/2 times log with base absolute x of that quantity. So we obtain 1/2 times log base absolute x of 2x minus 1 equals 1/2. Next, multiply both sides by 2 to match the image's next line. We get log base absolute x of 2x minus 1 equals 1. Converting this to the equivalent exponential statement, as shown in the image, 2x minus 1 equals absolute value of x. Following the image exactly, solving 2x minus 1 equals absolute x produces 1 equals absolute x produces 2 listed candidates. We record x equals 1 and x equals 1/3. Finally, we check these against the full logarithm requirements. The base conditions already listed rule out x equals 1, since the base would be 1. Also, the argument 2x minus 1 must be positive, which requires x greater than 1/2, ruling out 1/3. Therefore, just like in the image, the solution set is empty. Example, we will solve the logarithmic equation, log base x squared of open parenthesis 2x plus 1 close parenthesis squared equals 1. We will follow the exact algorithm shown, step by step. Step 1. State the base conditions. Because the base is x squared, we must have x squared greater than 0, and x squared not equal to 1. Step 2. Use the power rule carefully, moving the exponents from the base, and the argument gives 2 over 2 times the log base absolute x of absolute 2x plus 1 equals 1. Step 3. Convert the log statement into its exponential form. Log base absolute x of absolute 2x plus 1 equals 1 means absolute 2x plus 1 equals absolute x. Step 4. Solve the absolute value equation by cases. Case 1, 2x plus 1 equals x, which gives x equals -1. Case 2, 2x plus 1 equals -x, which gives 3x equals -1, so x equals -1/3. Step 5. Check against the base conditions. The value x equals -1 makes the base x squared equal 1, which is not allowed. Therefore, it must be rejected. The value x equals -1/3 is valid. Hence the solution set d equals the single value -1/3. Summary. We stated the base restrictions, used the power rule to obtain 2 over 2 times the log base absolute x, turned the equation into absolute 2x plus 1 equals absolute x, solved by cases, and kept only the value that satisfies the domain. Final answer x equals -1/3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.